Okay, can you just confirm that you can see this this T-table example?
Yeah.
Okay. Now, you need to have your T-table open in front of you from the data sheets. I've only got a small section of it here, degrees of freedom 1 to 14. You need to have the full thing in front of you. So, this example here for T-tables. For the following, complete the data by determining the p-value, if the difference between the means is significant or not, and the decision about the null hypothesis. So if we start with the first one, what I want you to do is go to your T-table and use the degrees of freedom of 10. Now that would be based on a sample size of 6 and 6, very small in the two sample cohorts. -2 would give you 10, degrees of freedom 10. And the t-value is 2.280. So could you quickly determine the p-value, whether the difference is significant or not, and the decision about the null hypothesis? I'll wait 1 minute. Okay, so for this first example, using your T-table from your data sheets, a degrees of freedom of 10 and a t-value of 2.280. If I go across the row at 10 degrees of freedom, I get to 2.228 in the column of 0.05 probability. And then if I go to the next column, it's 2.764. So the figure that I've given you here of 2.280 lies between those two figures. So therefore, the probability value is less than 0.05 if I go to the top of that column, and greater than 0.02. Is this a significant difference between the means? Yes, because the probability the results are due to chance is less than 0.05. What would you do about the null hypothesis? Well, a null hypothesis will state that there is no significant difference. So you would reject the null hypothesis because there is a significant difference. Now, at this point, does anybody want to ask a question before we go on to the next example? Now you'll have to unmic and ask me the question as I have the information in front of me. Okay, let's try the next one. Degrees of freedom 20. The t-value is 1.980. Same thing again. Determine the p-value. State whether the difference between the means is significant or not, and then the decision about the null hypothesis. I'll wait 1 minute. Okay. For degrees of freedom of 20, if I go across there to try to find 1.980, then I see on the first column 1.725, but my figure is bigger than that. The next column 2.086, and my figure is smaller than that. So it's in between 1.725 and 2.806. So my p-value is greater than 0.05 and less than 0.1. My decision is there is no significant difference between the means because it's greater than 0.05. And my decision about the null hypothesis is I would accept it. Okay. Number 3, oh, sorry, at that point, is there anybody who wants to unmic and ask a quick question? Okay. Can you try number 3? Degrees of freedom 30, t-value 2.850. Okay. For degrees of freedom of 30, and I'm looking for 2.850. If I go across, the column that I start getting interested in is 2.750 and then 3.385. So my figure here of 2.850 is greater than 2.750 and less than 3.385. So it's in between those two. So then if I go to the top of the columns, the p-values, what I can say is the p-value is greater than 0.002 and less than 0.01. So the fact that it is less than 0.01 means it's certainly less than 0.05. So the difference between the means is significant. The decision about the null hypothesis, you would reject it. And then I'll do one more and then I'll leave one for you. So the last one I'll do is degrees of freedom 40, t-value is 3.310. Okay. For 40, if I go across the row there to find 3.310, then I can see it's going to be between 3.307 and 3.551. So it's in between those two figures. So my p-value is less than 0.002 and greater than 0.001. So before we move off this exercise, I've left one for you to try by yourself and see how you get on, and maybe then come back to me if you have any further issues. At this point, does anybody want to ask a question to clarify what I'm doing here in this exercise using the t-table?
Could I just check when exactly do you reject the null hypothesis?
Okay, so you reject your null hypothesis when your p-value is less than or equal to or less than 0.05, because your null hypothesis states there is no significant difference. So if you have a p-value from your t-table of 0.05 or less, that means you have calculated significant differences between the means, and therefore you can reject your null hypothesis.
Thank you.
Does that make sense?
Yep, and if it's less than the 0.001,
then it's highly significant, because
okay,
anything less than 0.05 is significant, and then as you go across the table, it gets more and more and more significant.
no problem, thank you.
Okay. So if we move on with this, we finished here yesterday on this example. Now, I'm still expecting people to come back to me with their working out of this example to make sure they agree with the t-table that I have here. So far, we have about 4, maybe 5 students that have come back and shown me this example and wanted to work through it. But I would recommend everybody try this to make sure they're doing it correctly. Now, the last part of the statistics section is this chi-squared, or you might even pronounce it chi-squared in your schools. This formula is in your data sheets. Chi-squared is equal to the sum of the observed results minus the expected results squared divided by the expected results. And for the degrees of freedom to use this chi-squared table, you use n minus 1, which is the number of categories that we're using. The degrees of freedom, as stated there, is the number of categories minus 1. The p-value, the probability that the difference between you don't need to use means in chi-squared, so ignore that wee bit. This is just a continuation from the t-test. The probability of the difference in the means by the t-value is calculated due to chance. That's applying to the t-test and not the chi-squared table. Critical value, once again, is always 0.05, where 5% of the differences between the results are due to chance. And the p-value greater than 0.5 means there's no significant difference between the means. Once again, if we're using means, we're applying it to a t-test. The difference is due to random variation. A p-value equal to or less than 0.05 means there is a significant difference between the means. The differences are not due to random variation or chance. A chi-squared table is in a similar layout to a t-table, degrees of freedom on the left-hand side, probability values on the top, and the most important probability value is here, 0.05. Now this time you'll see on a chi-squared table, there's also 0.5. You have to be very careful not to confuse those two, because this is the critical value, 0.05. So if your chi-squared value lies on that column or to the right of it, you're going to be able to say that the difference between your observed results and expected results is significant. It's not due to chance. It's not due to random variation. It's hopefully due to something biological that we are studying. Now, an example. Males, so we're using gender here. Now, at this point, I must remind you as well. If we look at some of the factors, chi-squared is a discontinuous variation example. So you're looking at, for example, gender, male, female. Smoking, smokers, non-smokers. You can do chi-squared. Alcohol, drinkers, non-drinkers. If you're calculating numbers in cohorts, the number above an average and the number below an average, for example, in weight, if you have an average weight calculated, you could say, do the males above the average weight have a significant increase in CVD than the males below? Then you have two sets of numbers. That's still chi-squared. So you're going to be able to, or even age, above 65, below 65. But they're discrete data examples. And the most important thing in the chi-squared test is being able to calculate the expected result. So you see here from this formula, you're going to have observed results, and you have to have the means of calculating an expected result due to some logic. Once you calculated the expected, then this formula here is very easy to apply. And remember, you can be doing several chi-squareds and get the sum of them, depending on the example you have. So if I go to this example here, males in the example in the 262 master copy sheet, 262 patients. If we just look at the males with CVD, 85. Males without CVD, 59. Now, if I'm trying to calculate an expected result for those two groups, I have to use some logic. So I'm trying to see if gender has an impact on CVD. And I can see here, males with it, 85, males without it, 59. What if, to calculate my expected results, I'm saying to myself, well, gender has no influence. Well, what should these figures have been? Well, they should have been equal. So if I want to get my expected result, what I would do is add 85 and 59, get the total, and divide it by 2. So there should have been half and half here. Same with the females. I can do 38 plus 80 and then divide by 2. So if we go to this one, look at what we've done in the chi-squared example. 85 plus 59, 144. Divided by 2 gives you 72. So the expected result for males with CVD is 72. The observed result is 85. Without CVD, observed 59, expected 72. And then I calculate a chi-squared. Now, once I've got an observed and expected, I have a very simple formula. Observed minus expected squared divided by expected. So if I go back to this, that's all I did here. Observed minus expected squared divided by the expected to get 2.35. I do the same for this one. Observed minus expected squared divided by the expected, 2.35. And then because this is sum of, add them up, I have added 2.35 and 2.35 to give me 4.7. Now, once I get 4.7, I can then go to my chi-squared table. And if you look at your chi-squared table there in your data sheets that you have open from the CCEA website. So what do? You go along and you have to decide, first of all, in order to use your chi-squared table, what's your degrees of freedom? Well, we've only got two categories. We've only got with CVD and without CVD. So our number of categories is 2. Our degrees of freedom is the number of categories minus 1. So the degrees of freedom that we're going to use on the table is 1. So now I've got 1 degree of freedom and I'm looking for a chi-squared value of 4.7. So go across the top row to try and find 4.7. And I see it's between 3.84 and 6.63. So therefore, it is less than 0.05 and greater than 0.01. Is there a significant difference? Yes, because it's less than the difference between the observed and the expected is significant because the probability value is less than 0.05. There are less than 5% of the results due to chance. So the results are significant. So is there a significant difference? Yes. The null hypothesis, rejected. And then for the females, I did exactly the same. Observed minus expected squared divided by expected, 7.47. Observed minus the expected squared divided by expected, 7.47. Sum of 14.95. Degrees of freedom 1, 14.95. Much bigger chi-squared value right off the end of the row because the biggest value we have is 10.83. So our p-value is less than 0.001. Significant difference? Yes. What would we do to the null hypothesis? Reject it. Now, as I said to you, this is about discontinuous data. So some of the examples that you are dealing with, if I go to the biomedical cohort, gender, as I said, male, female, or even when we go in here, males with or without. Smoking, smokers, non-smokers, or smokers, non-smokers, and previous smokers that have stopped. You can still put them into 2 groups or 3 groups if you want. Weight, above and below the average weight, or above and below a certain weight that you want to pick. Alcohol, drinkers, non-drinkers, or even in alcohol, the drinkers categories, category 1, 2, 3, and 4, because they're broken up into categories in terms of how many units they take per week. Age above and below certain ages, creating two categories. You could even do it with blood pressure in that you could put above and below a certain blood pressure, the risk of CVD. But you can see what I'm trying to do here. This is not based on averages. This is based on presence or absence. This is discontinuous data. The t-test and the chi-squared is about continuous data. Now, before I just stop this quick presentation and answer any of your questions, can I also remind you, people have been asking what to put in this section of results. So in the results, if you have 3 factors, you should be able to have at least 2 either chi-squareds, t-tests, and 95% confidence limits done across the factors. So what I would expect is 6 pieces of statistics done. 2 chi-squareds, 2 t-tests, 2 95% confidence limits, or a mixture of those, because some of your factors may not lend itself to chi-squared or t-tests or 95% confidence limits. But I want to see a mixture across all 3 factors, and start general, the biggest cohorts. High cholesterol, average cholesterol, say for example, average total cholesterol for patients with CVD, without, and then start going into smaller specific questions. Males over 65 with increased cholesterol, is it significantly different than males under 65 with low cholesterol? You can start asking yourself more specific questions and do as many as you want within your group, but start general and then work your way into more specific. And I want to see at least 6 across the stats.